Okay, so I'm going to talk about a methodology today called life cycle assessment, which is an engineering-based methodology for taking a systems perspective of typically the environmental impacts of an energy technology or another technology. And I put systems in quotes here because I'll describe what I mean by that, and I think you'll see by the end what I mean by that. I don't need to do the lecture overview. Life cycle assessment is a little bit abstract if you don't have a sort of an application for it. So I thought it'd be useful, instead of actually just sort of running through theory, it would be to run through an application which relates to run through an application and explain how life cycle assessment is applied in this application. The application here is something that I've been involved with a lot over the last couple of years, which are regulatory efforts to reduce CO2 emissions from transportation fuels. So in California, there's a regulation called the Low Carbon Fuel Standard, or LCFS. In the EU, there's a similar EU-wide regulation called the Fuel Quality Directive. Both of these regulations attempt to reduce the CO2 intensity of transportation fuels. So this is not not improving the efficiency of vehicles to reduce CO2 from vehicles. It's actually taking the fuel and trying to reduce the fossil carbon content of those fuels. As it turns out, it's actually an enormous challenge to track the carbon emissions from producing a fuel. This is, to call it non-trivial is sort of an understatement. Part of the problem is that fuels are produced in complex supply chains, sometimes spanning multiple countries around the world. Emissions come from multiple industries, multiple processes, and the emissions are often difficult to measure, particularly from bio-based pathways. The metaphor here that I'm going to use to sort of frame life cycle assessment is due to, you can't read it very well down there, a colleague of mine named Richard Plevin, who's at UC Berkeley. He's a professional researcher there. And he uses a sort of a mathematical analogy. It's a little loose, but I think it gets at the sort of scale and dimensionality problem. He describes sort of simple traditional engineering calculations of emissions from a process as being point emissions. He then describes, you can sort of take this point and sort of stretch it out and think about complex interactions of multiple processes or multiple engineered systems. And so he describes this as sort of you're moving from a one-dimensional point or a zero-dimensional point to a one-dimensional line. And then what people are doing now is moving beyond this sort of this sort of line metaphor to what he calls the plane, where you have multiple complex indeterminate interactions that can be political or economic in nature that mediate this otherwise straightforward process. And I'll give an example of each of these and how these affect your ability to compute the emissions from a fuel. And I think the example will be clear. Point modeling, as he describes it, is process modeling of a single facility or technology. We've got a car, we draw our process boundary around the car. Mass and energy enter the automobile in the form of fuel. We intake air for combustion. We emit CO2 out of the tailpipe, and energy is released, and our car can go. We might also, in this point sort of framework, model a boiler, model combustion in a boiler to understand soot formation, NOx, SOx, traditional pollutants, heavy metal emissions, things like this. Or we might ask questions like, how much CO2 is released from an automobile tailpipe per kilometer traveled? This is a much more, this is not a systems perspective, this is sort of a device level perspective, okay? And you're modeling a single device at a time and drawing fairly constrained process boundaries. If we're to do this with gasoline and corn ethanol or maize ethanol here, and we're going to track fossil CO2 emissions, for every megajoule of fuel we put into a vehicle, we get about 73 grams of CO2 out, of fossil CO2 out from burning gasoline, and 0 grams from burning corn ethanol. Why 0 grams of fossil CO2 from burning the corn ethanol? Where does the carbon in that ethanol come from a corn plant? Yeah.
Current solar income if you discount the tractors and the processing.
Yeah, I'll get into tractors and processing, but yeah, it's basically solar energy that's captured by the plant. Plant reduces oxidized carbon, and that's from the atmosphere, reduces CO2 to form biological compounds, which then we transfer into fuel. So that carbon was basically in the atmosphere this summer when the corn was growing in Iowa, and you take it and you burn it in your car. So that's not fossil carbon, so that's got 0, okay? However, life cycle assessment says, well, you can't look at any process on its own. In order to drive my car, I actually had to have a refinery, I had to have an oil well, etc. This sort of metaphor, this line, you can think of as sort of a line as a series of points. So you take a series of points and you construct this process chain. So you might say, you might ask, what are the total impacts from all stages of a product life cycle? And that's where the term life cycle assessment comes from. Typically, this is done, you look all the way from manufacturing, from raw materials, to transport of products, to usage of products, and to disposal of products. Disposal doesn't really apply in this case because the exhaust just goes out the tailpipe, but in terms of physical products, things that you throw away, it takes energy actually to dispose of them or recycle them, and these sorts of things have to be tracked. And so this product life cycle can be thought of as a series, approximated as a series of point processes, each of which can be modeled individually. So here's a pathway for ethanol. So we can break it into sort of three categories. So here's upstream, refining, and consumption. Consumption occurs in your automobile, you have fuel consumption. Before that, you have to ship the finished fuel to the car. Before that, you had to make the fuel in a biorefinery, so you had to make the ethanol. Before that, you had to get your corn to the biorefinery. Before that, so again, we're sort of tracing up this line, right? We're moving back up this pathway. We had to harvest the corn, we had to grow the corn, we had to clear the land. As someone mentioned, fertilizer, you had to drive tractors, fertilizer, this chain goes on and on and on. In actuality, this should raise a question. All of us were thinking critically, although it's 2:30 in the afternoon, which is a rough time for all of us, but sort of we're thinking critically and we're saying, where does this line begin and end? It's actually hard to sort of draw a boundary. Do we count the fuel used to drive tractors on farms? Do we count the energy used to build tractors for farming? How about feeding the workers who built the tractors to farm? How about natural gas consumed to make the fertilizer used to grow the food to feed the workers who built the tractors that were drawn on the farm? It's like the children's rhyme of the cat that ate the fly that it said, I don't remember what it is, right? Where does it end? And the kids like it because it's this sort of nested problem. This is typically called the truncation problem, where you have to select process boundaries and say, this is what I'm considering the impacts from, everything else I'm neglecting because it's small. And this is a major problem and a source of error, and people look at this a lot. You can see here's another diagram of these higher order inputs. So maybe into energy crop growth, we have diesel, we have nitrogen fertilizer, we have irrigation water. In order to make fertilizer, we needed natural gas and steel. If I went further, in order to make steel, we would need natural gas and coal maybe. What ends up happening is actually this doesn't look like a line. It looks like a nested, interconnected set of processes. So the line, that's why the line metaphor doesn't work super well. A quote here I like from a guy who was far ahead of his time, John Muir, in 1911 said, when we try to pick out anything by itself, we find it hitched to everything else in the universe. Okay, so this is this sort of, it's almost sort of an ecological perspective. It's almost the ecology of engineered systems. There's all these interacting processes, right, that can't necessarily be separated from each other. As it turns out, we've got math, as it turns out, there's actually an infinite number of interactions. This type of mathematics was first solved, a guy won a Nobel Prize for it, for applying similar mathematical framework to the interaction of economic sectors. And that's where this mathematical framework was sort of inspired by. But you can write any process as a column in this matrix, and each product or each row in the matrix corresponds to a product that has a given unit. So this first product might be megajoules of natural gas. The second product might be kilograms of coal, etc. So each row has a given unit, and each process has, via sign convention, either inputs or outputs of each process or each unit you're tracking. So basically, it's a mass balance of multiple processes written in a matrix framework. You can then scale for some final demand vector. Let's say I have 1 unit of ethanol down here. By inverting the matrix, I can calculate what the total inputs are required to make that 1 unit of ethanol. So this is basically how this is done in practice. As you might imagine, there's all sorts of complexities involved in doing this correctly. But that accounts for these infinite number of interactions. If you do this reasonably correctly, you're going to get a different answer. So here's 2 pathways. This goes from an oil well to an oil refinery to your car. This goes from a corn plant to a biorefinery to your car, and you get quite different numbers. You go to 98 for the gasoline pathway, and you go to 81 for the ethanol pathway. So instead of 70 and 0, you're now at something like 180. So a lot of the advantage of the ethanol pathway goes away because of these portions right here, growing the plant, and then the biorefinery is quite energy intensive. You can ask about that negative term in the questions. I can tell you about that. Unfortunately, we can't separate out any one process from any one sort of set of nested engineering processes from the broader world. I now have these sort of squiggly lines. These are indirect interactions. This is a massive research effort right now. Lots of people are working on this around the country to try and understand these interactions. It's very complex. So we might ask, what are the indirect impacts that might be mediated by policies and human actions? To give one example, biofuels are produced on a planet where 7 billion people live, and all of them need to eat. So expanding biofuels production with corn or with other food products affects people everywhere. The U.S. is a massive exporter of crops around the world. We feed a lot of people in other countries. And so if we use more ethanol or more corn for ethanol, there's less to be exported. This then induces people to plant more crops elsewhere, because they're no longer able to import from the United States. This is called indirect land use change. And the problem is that this is only partly a physical or sort of engineering question. It's really sort of a human factors question. It's an economics question. It's a policies question. It's all sorts of, it's got lots of things tied up into it, and you can't basically analyze it under this previous sort of matrix framework. Here's an example of some results from a model. So this paper from 2010 asks, where would land conversion occur if the Brazilian government instituted a biodiesel target? Say we have to have a certain amount of biodiesel for our vehicles. This is the case that they ran for soybeans. Okay, and they found that soybeans were planted in this region in Brazil. This is the Amazon rainforest. Soybeans were planted here. This is where the direct soybeans would be planted, so not much destruction of the rainforest associated with this target. Unfortunately, what was there now has to go somewhere, and so they found that, and this was based on an economic model that they used that included land cover and land types. You see this indirect land use pushes into the rainforest, and this is one of these things that's extremely difficult to model. There's lots of these potential effects that are challenging. When you add in this number here, this indirect number, hugely uncertain, 10 to 100, you're going to get somewhere roughly equivalent to gasoline or significantly worse. This, in the last 5 years, has totally changed. This type of research has totally changed our opinion of corn ethanol. It used to be viewed as a positive thing. It's largely viewed negatively now because of these sorts of effects. Cellulosic ethanol and other advanced ethanols don't suffer from these similar problems to this degree. Okay, some insights from LCA and then a few questions. The scale and boundaries applied to your analysis can strongly affect your results. In this case, it flips the sign. If you look at it narrowly, gasoline is worse than ethanol. If you look at it from the broadest perspective, ethanol is worse than gas. Products can have large impacts upstream, so you can't just look at your device in your place. You need to think about what it took to get that to you. It's difficult to calculate exact emissions from any complex set of processes, and complex indirect interactions should not be ignored, because when you're thinking about environmental impacts, you need to think broadly. We're going to have a seminar, a class, where you guys can learn more about this. Energy 295, it's going to be offered in the spring, Quantitative Environmental Assessment of Energy Systems. I'm going to co-teach this with a couple postdocs from GSEP. And Mick Dale and Charlie Barnhart, and it's gonna be a seminar class, sort of 1 to 2 hours a week, readings, a little bit of problem sets, but mostly discussion of these issues. It's an interesting area, and lots of interesting questions are raised by it. So I don't know how I did on time, so questions maybe.
One of the themes in this research kind of alludes to the broader work by Norgard that you probably were working with here at Berkeley, on the co-evolutionary economic model, and looking at all variables and interactions between them. One of the problems that you were also mentioning is the endogeneity between these variables, and so it's very tough to define the start and end. It's also tough to assess the causal relationship. So what methods do you think are best to look into this? Because like autoregressive methods are great, but we don't really have data on that in this area, it looks like.
Yeah, let's see how specific I can get about that. With regard to sort of a simple engineered system, it's relatively straightforward, or simple engineered, an interacting set of engineered systems, that's relatively straightforward. That math has been worked out. There's a lot of uncertainty with regard to, you're modeling it as a system of linear equations. There's assumptions implicit in that with scale, and as you really scale an industry, it may not scale linearly, right? This is just an approximation of how the economy works. With regard to interactions sort of outside of this matrix-based framework, that's where things get really tricky. Right now, there's a lot of LCA people who tend to be engineers by training or physical scientists interacting with economists. It's not clear to me how you actually couple these systems together yet, and I don't know. It's one of the things that I think about, like when I'm jogging in the morning. It's sort of one of these philosophical questions of how would you actually do that and make the math work. And I don't even know what else I can say about it other than that. Other than I don't really have an idea, and people are working on it. But it's incredibly complex. Even if you include the economics, then there's policies and social factors and all sorts of social acceptability of going into the rainforest, right? Social norms like should you be able to go into the rainforest and clear land, should you not? Poverty, there's all sorts of issues. It's incredibly complex, and I don't know how to capture them in equations, and I don't know if that's actually the right framework to think about these things in the end. Yeah. No. Questions? Short answer. Come on, questions about Stanford. It's questions about grad school, Phil. I know this guy, so I can pick on him by name.
So, ethanol is obviously a really good thing to do a life cycle assessment on because it shows us that it's actually not good carbon-wise. We might have thought otherwise. Are there other big fields that need to have life cycle assessment done and haven't had that, or that there's research going on?
There's little that LCA hasn't been done on. There's areas where it's weak and could be improved and things like that. It's most important where impacts don't occur on site. So basically all renewable energy technologies, if you want to do an environmental impact assessment, you need to do LCA. You're not looking at the question from the right framework if you're looking, oh, my wind turbine produces no carbon, therefore wind is carbon free. This is not actually true. Depends on where you made your turbine blades, how much steel did you use, how much cement did you use, what was the installation energy. Wind is actually very low carbon, but it's not zero, right? And so typically renewable energy technologies, because they're, you're putting capital in place and then the capital it runs without emissions, you really need to look at what's required to build that device rather than sort of the on-site emissions. And so pretty much any renewable energy technology, you need to use LCA. And it's been done widely. It's varying levels of quality, as I said. I'm not intimately familiar with most of the literature. There are big gaps in the fuels literature. I've been doing a lot of work on oil, and the way oil life cycle assessment was done until recently was pretty poor, and I think we're making strides on that here, doing that in more detail, getting into the sort of engineering details for how oil is produced, what are the fugitive emissions, these sorts of questions. Those are the ones I know about, and I'm sure there are lots of gaps. Michael Peck would know about. He does infrastructure. He's a civil engineering professor who teaches a life cycle assessment class, and he looks a lot at building materials, cement versus asphalt. What do you build things out of in order to reduce the environmental impacts? Because there's a lot of energy we use just to create materials to build buildings and roads and things like that, and he looks at that.
You talked about how you look at things upstream of new technology, but what about downstream of that technology? For example, in some organic solar cells, they have it. It would be about 6 years, so that's plastics that would go somewhere.
Yeah, that's an excellent question. So typically what's done is for a physical product rather than a fuel, you need to track it basically to the end of its life cycle assessment. You the ideal process boundary is from when the primary materials leave the natural environment to when they essentially return to outside of the human system. It's a little bit of a strange distinction because it's not clear sort of where the human system ends and begins. But in that case, you would need to account for the life of that panel and say, well, it uses a lot less energy to make thin film. Oh, but I'm only dividing that by 6 years of energy input or energy output rather than 30 for like a silicon PV system, for example. So you're dividing your embodied energy by less energy output. And then you would also need to track basically the mass of that panel and where does it go? How much of it is recycled? How much energy is saved if it's recycled? So do you save a lot of energy or a little energy? How much of it is unrecoverable? A lot of these things, parts or wholes of them are unrecoverable and you just can't reuse it very well because it's manufactured in a way that you can't disassemble it or it ruins the properties of the material if you try to recycle it. So you would need to track all of these sorts of things, and that would include the disposal stage, and so you would want to do that.
Under your work, you studies that talk about essential cost analysis of hybrid and electric vehicles. There's a lot of talk about how the batteries actually get that whole environmentalist primarily.
Yeah, there's a bunch of studies that have been done on it. That's something that was done a fair bit, let's say kind of 5 to 3 years ago. There were a number of papers that came out. I think the best one is out of Carnegie Mellon University. It's actually first author, his last name is Samaras, Samaras, if you want to look that up. And they include the battery manufacturer component on that graph, and it ends up being very small. Those numbers are typically blown out of proportion largely for political reasons because people are trying to make a case against hybrids or fuel efficiency for whatever, in my humble opinion, misguided reasons they have for doing such things. They sort of, I think the battery issue is largely a straw man. There's a lot of embodied energy, but also a hybrid saves a lot of energy over its lifetime, and so they did the division properly, and it's on order, if I recall correctly, kind of a 5% effect. It doesn't, it doesn't make or break the hybrid case.
Yeah, are there has international standard aggregation protocol helps address sort of how far to go upstream in terms of programs to address or currently so sort of sector and that standards for
Yeah, sorry, what? Maybe you can repeat the question. Oh yeah, so I'll repeat the question. So the question was, do international greenhouse gas accounting standards or any other sort of regulatory framework sort of specify how far up this production chain you need to count in order to get an official number or sort of standardize this? And is it variable enough between sectors that you can't sort of make hard and fast rules? So it is variable enough between sectors that it is difficult to make sort of hard and fast rules. This is all, at the level you're talking about, this is all extremely politically negotiated. So for example, I've the last 2 days I've gotten a whole flurry of emails from Europe where a report was leaked, which whenever these reports are leaked, it's sort of, well, it was actually sort of purposely leaked to pre-warn the press that something was coming, that Europe was finally going to start looking at indirect land use change. So their biofuels targets have not looked at indirect land use change. In the US, we've been looking at for a couple of years. This is one of the rare cases where the US is ahead on life cycle assessment and tracking these things. And they, as part of their regulatory and political process, have basically ignored it until it's now leaked that they're going to start to think about accounting for this in their regulation. So right now, their regulation doesn't say, for example, so they use a ton of biodiesel in Europe, which is perhaps a good thing, except a lot of this is palm oil biodiesel from the tropics, from Indonesia, Sumatra, these places. And you can find pictures of massive land clearing, really terrible stuff going on to produce biodiesel, and it just doesn't seem to be sort of efficient. And they haven't included that in their biodiesel targets, and now they're starting to include these land use change, or they're going to, in theory, they're going to start to consider these land use factors. So once you start thinking at the level of sort of national and international regulatory processes and standardizing things, it becomes very negotiated, and farmers and fuel providers and everyone else has a say at the table, and people argue about what should be included and what shouldn't. And so it becomes, and this is where science can come in and say, hey, look, we are seeing this land conversion happen. We have satellite data, or we have these other data. So.
Okay, I take one more question. Do you have a question? Yeah.
Have you looked much into LCA for natural gas production use? Because I know there's been a big controversy over the past year over what the emissions are from that.
Yeah, this is a very good question. So huge controversy over that. So for those of you who aren't familiar, there's been a lot of controversy over natural gas produced via hydrofracturing. So it's been a big deal in the U.S., reduced gas prices significantly. There's a glut of gas right now. We have more gas than we know what to do with. Historical low prices. There's been a lot of controversy over what the fugitive emissions are from fracking. Is natural gas going to get worse because we're now fracking for it? I've managed to, so far, to date, stay free of that debate. I have embroiled myself with a couple projects this coming quarter and in the winter quarter. I've signed on to sort of an expert panel. We're going to review the data and come out with a sort of a sense of the consensus of the literature so far this fall. And I'm definitely going to be working on natural gas more. I kind of can't avoid it because it's such an enormous issue and such a big deal. But that's certainly a topic of big controversy and interest. And natural gas is huge because I don't know if you guys know the amount of coal-fired electricity that the U.S. generated has dropped more in the last couple of years than it has in decades. Really rapid drop, basically because gas is so cheap that people are saying, I'm just going to turn off my coal-fired power plant and run gas. And so this actually has been hugely beneficial from the electricity sector emissions perspective. And so the debate is whether or not this fracking actually makes the natural gas. A guy from Cornell argued that the fracking makes the natural gas worse than coal, and that's what really set things off. Congressional hearings, all sorts of kind of high-level controversy. New York Times gets involved and reports on it, and then it's just a storm. And good luck to anyone involved once the Times or the other sort of national papers get involved. So that's been very controversial. Very interesting questions, and I don't have a sense myself of where the data lie on that.
Okay, next, thank Professor Brandt again.